Hmm. Okay. All right. So yesterday we left over here at trees, and we decided to pick up trees itself today. I'm not sure now if you guys want. I guess I'll just up to 60 FPS. BRB. Okay, awesome. Okay, so we. Oh, this is much better for some reason. At 60 FPS. Um. Okay, so we left with trees yesterday. Let's pick up from there. Um. Symmetric tree given a binary tree, check whether it is a mirror of itself. symmetric around center. For example, the binary tree is symmetric, but the following is not. Okay, so basically, if it's a mirror. Hmm. Hmm. Okay. So, yeah. So simply, I think if on first glance, it's sort of obvious that if for every node the left child is equal to the right child, and hmm, and sort of recursively repeating that. I'm not sure how to explain it. Let me see if I can write that down, and then it would make more sense. So is symmetric. All right. So so let's make a helper function. Helper. Just pass the root node in that. Helper. I don't know. Maybe it'll return true or false. Probably yes, it will. And we pass. Okay, so what we're gonna do is compare uh, two nodes each time for every node. Um, and what do you want to compare is, okay, so if left is equal to null and if right is equal to null, return true. That's one base case. Um, else if left is not equal to null and right is not equal to null, they both have value. So return left value is equal to right value and helper. So left, the left node of our left and the right node of our right are same, and the right node of our left and the left node of our right are the same. So basically, if you're comparing these two nodes, the left of this, which is 3, left of 2, which is 3, should be equal to the right of this 2, which is 3, and the right of the left node, 4, it should be equal to the left of the right node, which is 4 again. Or in case either of the two nodes is null, like only one of the two nodes is null, uh, which means it's wrong, and we found some mismatch, so it would fail. I think that should be. It's just a pretty simple question. I have done it before. Not gonna lie. Um, yeah, I freaking knew it. If root is null, ret return true, I guess. Yeah. So yeah, cool. So basically, a very simple recursive problem. You just check if the left node of uh, the left node of your one node is equal to the right node of your one node. So you might not be able to think that this would work for subsequent children, but it would if you actually draw it and see. So in here we'll be comparing for the first helper function this node and this node then, which is what we actually have to compare down the line. The left and right should be the right and left of this node. So yeah, if you draw a tree, you'll actually be able to see that it is going to be correct, this solution. Okay, don't name your functions helper. Awesome. Maximum depth of a binary tree. Again, this is also very straightforward question. Given a binary tree, find max depth. Max depth is the number of nodes along the longest path from the root to the farthest leaf node. Okay, so of course, again, we're going to use a helper function to calculate the height. Um, so what's it going to be is if root is null, uh, return 0, and then helper root left, root right. At each step, what we're going to do is return the height of the left node and the right node for each node, for its left and right node, and then we're going to add 1 to it and see which one of those is bigger, or whether the height of the left node is bigger or the right node, and we're going to return the bigger one. So basically, it's going to recursively call this function for each of its child, both of the nodes left and right, till we reach a null, and that's going to be our base case where we're going to just return 0 or 1. Okay, left. If that did not make sense, then I'm sure when I write something down that will. Okay, so left and right. If left, okay, let's keep two variables, int left height, which is 0, and right height, which is 0. Sorry. If left is not equal to null, um, um, left height is equal to temp, sorry, is equal to helper of left, left, and left, right. Um, Same thing for right node. If right's not null, the right height would be right, left, right, right. Um, and then return max left height, right height, plus 1. Just run this. Okay, this is probably going to be like a difference of 1 or something somewhere. Sorry. Mhm. Invalid conversion from. Sorry. Hmm. Oh, it worked. Awesome. Cool. Now this is a recursive solution. Not sure if there is going to be a iterative solution. Mm, yeah, there probably is. I don't think we even have to look at any of these. So what it's going to be like, so just iterate till just while true. Keep going to the left and right nodes. Actually, hmm, we don't know how much to iterate. Oh yeah, so it's going to be like BFS. So instead of recursively moving down a function, you push your values into a queue. Uh, if you do not know how BFS is done, we'll come to a question for sure soon enough. So basically, you start with the node, add the children of the current node. So basically, you add the root node in your list, and then whatever's in your list, you add its children to the list and remove the existing one, and you keep doing that. And let's say for each such iteration, we increase our height by one. So first iteration we'll have these two. Second iteration we'll have four, maybe here up to four, then 8, 16, and so on. And when we reach the end of our tree's height, we'll be adding the last nodes, and then if we check if any of the last nodes that are the nodes in our list have any children, it'll be false, and that's when you break, and whatever height we set to at that moment will be the answer. So that would definitely take less memory, I think, because stack memory is uh, probably going to be more. Okay. Anyway, we'll come to that when we do BFS. It'll be it's pretty easy uh, once you've understood the concept. Okay, I hate this. I don't like traversals, but this is different, I think. Oh, given a binary, return the bottom-up level order traversal of its nodes values from left to left, level by level, from leaf to root. Okay, so this is actually BFS. I think what the solution I can think of is BFS. So like I just said, how BFS is done is you keep the keep every uh, l- all the items, all the nodes at a height in your list, and then you remove that item and add all the children of the items in the list. So if you can see, that is something that is pretty much what's happening over here, except that our return value is in the opposite order of the BFS. So since it's a vector, we can just reverse it in the end, and sort of removing our node, we can not remove it and use the last list in our list of lists, which is the vector vector int. So if that didn't make sense, again, let me just write it down and I'm sure it will make sense. So we're going to have a list that we'll be returning. So let's declare that. Actually, it's not going to be int, it's going to be this. We'll convert it into int later on. Um, if root is null. Let's take care of the stupid base case. Return ret. Okay, awesome. So our topmost element is going to be the root itself. So let's create a list of tree nodes. That's what's going to be inserted in our return value. Let's just call it temp dot pushback root, and we're going to keep iterating till till let's say the last list has any values. Yeah, so basically that, which is temp. um so while so actually what we need is a queue, because queues are first in first out, and if you see the order is from left to right, so we'll be adding from left to right, and then those uh, children of those nodes also we need to add from left to right. So it's best to keep a queue. That's what you actually use in BFS as well. So queue dot push, queue dot, okay, I'm not sure, is it queue dot, okay, no, so it's queue dot add, okay, just push, I guess. um, Root. So while queue dot size is not equal to 0, so we'll be using the queue for iteration and the temp for maintaining for the temp is what we'll be pushing back to our retval. So actually we can, I think, change this to int root value. Now we'll be iterating over the queue for int I equals 0, I is less than queue dot size I plus plus. Actually, we'll save the queue size over here so that we iterate only as many elements as there are right now, and even if we add any, they don't alter this loop anyhow. So if so auto t equal to q dot top, if hmm, t left is not equal to null, and then we declare temp every time, sort of here. Hmm. Let's just call it temp2. If it's not null, then we need to add it to the queue. And also we'll be adding key value. Then same thing for right. Now it's going to be done for all the nodes that we have. And then we're going to have this list filled. And once we have this list for all the current nodes in the list, we'll push that list to our answer. And that is going to be yeah, cool. I think that should be right. So basically what we did was queue was not declared. So can we not use queues? So yeah, okay, so again, access the last element. So it's front, sorry, you have to check from left to right. So the first element and pop probably hopefully pop removes the first element only. So now q dot pop as well. I think I've got that. Memory limit exceeded. Okay, let's see where that happened. So our we already have 3 in here, and the queue has this node. After that, the queue has let's t 3 and this. That's good. And our temp is um sorry. What is our ret? It's 3 920. Awesome. 15 and 17. Sorry, and 7 would be pushed. And then our queue becomes 15 and 7. That's true. Queue size is 2 now. Now 15 gets popped. Now since they're both null, go ahead. Queue is empty. That's awesome. Why is queue dot size? Well, let's just check if it's empty or not instead. while not q dot emtp. Oh, wow, I don't know how to say empty. Okay, while q is not empty, we keep doing that. And if not dot empty, yeah, that looks good. Mm, awesome. Oh, sorry, we had to reverse our answer also. So we just reverse. Cool. Welcome back, everybody who is coming back to the stream for the first time, and welcome to all who coming for the first time. Um, I am also streaming on YouTube today. Um, Again, first time streaming there as well. Um, uh, oh, I thought I was already streaming on YouTube. Yeah, yes, I am. Okay, sorry. Yeah, so this is the link, which is super weird to share. I'll just add that to my Twitch chat. Here is the link to the YouTube stream as well. Okay, cool. Um, so like I said, fairly straightforward. Okay, so this is BFS. I'll go through it again. So what we did was we took a queue, which is like just pretty much the same as a normal human life, real life queue. I'm sure you know about queues if you've landed on the stream. Um, and we push the first element in our queue, and then we add in every iteration, we add all the children of the nodes that we have in our queue and also remove all the existing items. So after every iteration, what you do have is the children of the current nodes in your queue. So for the first iteration, we started with 3 in the queue, and when we end, we are going to have 9 and 20 in our queue, and 3 is going to be removed. And whatever is in our queue right now, we are whatever is added in this iteration to our queue, we're also pushing it to another list and adding that list to our return value, because I think it's pretty clear that that is the list that you want in your return value, just reversed. So the reversing part we're going to do in the end. So we get 9 and 20. Now we check if 9 has any children. If it doesn't, then we just skip that. Then we go to 20. We check if it has a left node. Then we uh, pop 20 first, and then we add 19, add 15 to the queue, and also we add 7 to the queue. Um, Now we have 15 and 7. Same thing happens for both of them. Since they don't have any children, we don't add anything else. Instead, we just add these to our list and add that list to our return value. In the end, we'll get a list that has 3, 9, 20, and 15, 7. And then we just reverse that list and return that. Okay, I think that was fairly simple. Okay, next question. Convert sorted array to binary search tree. Oh. For this problem, height balance binary is defined as binary in which the depth of the two subtrees of every node never differ by more than one. Given an array where elements are sorted in ascending order and convert it into a height balance binary tree. Okay, so one approach is to start with taking the center element as the root node, and then considering the remaining left side of the array and the side of the array as same as the first, same as the problem statement, and then doing the same with those. Um, so you just create a node and return that. So our helper function would be returning a node, which we will be setting to the left and right child of each node that our helper function would be setting, which in the end would be returning a node to our root node, pointed to our root node. So to maintain what is the from and to index of the array subset that we're looking at to convert to a tree, we'll take two variables and okay, let's start writing. I usually don't like problems like these because I don't. Let's see if I'm able to solve this. I think I've never actually written the code for this particular problem, though I do know the solution. Okay, so we start with a root node being okay. So this is going to be a root node, and then we're going to call a helper function to convert some part into a um, into the left child of a node and some part into the right child of a node. So we need three things: the node whose left and right we have to set, the left index the of the left index of the left tree, the right index of the right tree, the left index of the right tree, and the right index of the right tree. Okay, we'll probably be returning root. This will not be void. This will actually be a pointer, like I said, because we're going to call it recursively and be setting the left and right child through this function itself. So this will be the root. This will be the left of left. I need better names. The start of left, the end of left, the start of right, and the end of right. Okay. Um, so now if start of left is equal to the end of left, so there's just one node. Oh, we have to send the array as well, sorry. How else are we gonna pick our data? So it'll be a vector int. Let's just pass by reference, so you can ignore that. Unless it says that it's not a constant, so it's gonna be fine probably. Yeah, sorry. Then we just create new object for the node. Auto node equal to new tree node. Nums sl, and you don't even have to create like this. You can just write return new object. Cool. Similarly, if sr is equal to er, again we can just return that with sr. In case they're not, then root left is equal to helper so you have to make a new object. One sec. So you have to make a new, so you have to still make the current node so int mid equal to mid left equal to sl. Oh, maybe not return here. Maybe set the root node root left. I'm not sure right now. And maybe we're gonna set the root right. Let's see what happens. SL plus SE, oh sorry, EL by 2. Um, New node auto node equals new tree node nums mid. Okay, we could just not do this instead. Because that give us the same result really. Although we do need to add a break condition then somewhere. So we just created this node. Now this will be to the left of root, but we do need to set the left and right of this node also. Um, oh, but we still need to check if SL is less than equal to EL. That is only when we'll be doing all this. So node, then we just call helper node. So we're not returning since we're passing the node. SL, so length is SL to EL. So SL and mid minus 1, mid plus 1 to EL nums. And we do the same thing for the right node. Right, ER, SR, ER. Okay, I hate, do we have a dark theme here? Okay, we do. That's good. I don't think we can change this though. Hmm. Hmm. This theme. Okay. ER nums looks good. Otherwise, they're just gonna be null. Uh, but actually looks fine to me. Okay, we don't need to do mid. No return statement. Yep, no problem. Ah, oh, okay. New tree node, my bad. What was the test case? Okay. I guess we can just debug. It's not a big test case either. Um, okay. We start with the size being 5, mid is 2, root becomes 0, step in, put a breakpoint here, SL as 1, mid becomes 0. Ah, we can't let mid be the left node. We can actually, doesn't matter. Um, so this is one possible answer, so it's fine. So node is now -10. Step over. So we're gonna have a right child, which will be 3. Cool. Um, which will fail for both cases. So we come out. We come out again. Um, oh, we haven't passed anything by reference. Oh, sorry. We haven't set these nodes as the left or right child of this root, which we also need to do. Um, hmm, so pass by reference. Reference. I'm not sure how this is how we do it because I'm stupid, as you all know. Um, root left is node, and in this case, root no matching function to call this. Okay. Okay, that's fine. Let's debug again. Let's play. Root is 0. Root is -10. Root is -3. Root is 9. Root is 5. Fails, fails. We go back up. We go back out. Root left is 5. That's fine. Sorry, what was? Okay. How's it? How's ER5? Hmm. How are they both 5 somewhere? Hmm. Because of added size, not size -1. Like I said, I'm a fool. Okay. Great. Um. So I think I did what I said. Um, I hate you if size is equal to 0, return new tree node. I don't know. What do you want? 0? There's no constructor that maps with that value. What, null? What? What do you want? Just return null, screw you. Okay, fine. Okay, yeah, so what we did was broke problem into subproblems simply. So took this as the initial root node and then took this array and converted this array into the problem statement, took its center as the root node, and then took the remaining left array and the right array as um, another problem and converted them into subproblems, so on and so forth. And whatever was the node that we were working on at the moment, which we took as the mid, we set that node for our left subproblem as the left child of our passing node. And so whatever this array returned, we set that as the left of this, and whatever this array returned, we set that as the right of this, and we did the same for all the subproblems basically. What I am confused at is why it took so much memory and why it had such a bad runtime. This is a little bit concerning. Um, do we have a solution? No. Okay, let's just look at the discussions. 16 MSC++ solution. I think I've pretty much done the same thing. Um, um, so um, yeah, basically, hmm, mm, so I did that in a single function, both left and right for each node, and instead you did that in two functions. Hmm, okay. Anyway, I think the logic's right and there ain't no flaws as such. Yeah, I think if you do want to take a lesson, maybe you could use this, as this makes a little bit more sense since you're not repeating this particular code again. This is literally the same code as this with different variables. Um, so yeah. Let's just refresh and see where we at. Okay. Balanced binary tree. Given a binary tree, determine if it is height balanced. If it's height balanced, if the left and right subtree of every node differ in height by no more than 1. Hmm. Okay, so again, looks like a simple recursive problem where you just compare the height of the current node with your height of the left node of your current node with the height of the right node of your current node, which again you find recursively. And if the difference is at best 1, then you can return true or something. So I think we'll need a helper function that checks and gets the height for us. Height of a node, int height tree node star. Um, if node is null, return 0. Otherwise, just return height height max of node max of height of node left and height node right plus 1. So what this will be doing if um, home if height of root left is equal to height of it's not about the height, it's going to be if they're balanced or not. Return is balanced root left and is balanced root right. So, and when is it going to be balanced? It is going to be balanced in case if height if root is equal to null, then just return true. If height of uh, root left is equal to height of root right. Um, Return true as well. Um, so that is the so what's gonna be the order? So you have to call this for each node, and how this is going to be evaluated is um, if the difference in the height if the difference in the height mm, is greater than 1, then you return false. Otherwise, oh no, hmm, you check if left and right are balanced. This looks right, feels wrong, looks right. Let's see. So it did work for where the maximum. Hmm. Sometimes what makes sense is right, you know, even if it doesn't feel or look right. Because your intuition is not how code works. It's how code works. How code works. Oh, I'm talking nonsense now. Yeah, the bottom-up ON's approach would be better. Okay, there's another method given, which is better. They're saying that I think this is worth going through. Um, which says that so it says to do DFS on each node and calculate the height of that node. If the node is if the height of that node is like the difference greater than 1, then return -1, else return whatever the height is. Oh, okay. So basically calculating height to each node, and what we did was if the height at each height of the left node and the right node is greater than 1, then we return false. Else we check if the bottom trees are balanced. In calculating height again, we iterate through each uh, node multiple times. I think that's a good solution, which says if, yeah, instead of just doing height, using height to just calculate height, also check if the difference is greater than one, and just break in the middle, sort of, you know. That makes a lot more sense, I guess. Nice. I think most interviewers would accept this answer as well, because this is what I've seen most people give the answer as. But if they're not satisfied with that, um, I think you should look for the other answer. Okay, minimum depth of binary tree. The minimum depth is 2, so it's basically when you find the first node that has no children. So this clearly looks like a BFS solution where you know, as soon as you find a node that doesn't, so you check each level. As soon as you find a node on that level that doesn't have a left or right, you break. Left and right, you break. So let's make a queue of 3 nodes, and then push root while not queue dot empty. Um, while it's not empty, int queue size equals int h equals to 1, queue size equal to queue dot size if for I equal to 0, I is less than queue dot size plus if um, auto t equal to q dot front q dot pop if t left is equal to null and t right is equal to null. Return h else if left if t left not equal to null q dot push t left and then q dot push, sorry, same thing for right. So we add each level if a particular number does not have a particular point of the node does not have a left and right child, then we return the current value of h, which is added after each level is completed, and we move on to the next level. And in case root is null, we return 0, and if the loop doesn't run ever, set h is 1 if you have a root node. Um, let's start it as 0. Yeah, that makes sense. So we encounter this, h is 0, we iterate through this, output expected to. The output was 0. That's astonishing. Probably some variable name or something I missed. So h is 0. T is the root node. q.pop. If they're both null, return h, else push those into the queue. Oh, you have to do that after the for loop actually. Oh, never mind. It's fine. Oh no, that would be each node would be doing that. Yeah, sorry. Q dot it's queue size. Yeah. Okay. Now I don't mind debugging. So h becomes 1, queue size is 2. Hmm. I am hoping this is right. Yep. So this was ON. Basically, when we found the first node at a level that didn't have any children, which means that was the first leaf node, so we uh, just returned the code from there, and the h was set to wherever whatever levels we had covered. So we added those +1 to it because the leaf, because that node is one level down. Um, let's just check if there's any better solution. Oh, 1 line, 2 line. Wow, my God. Oh no, that looks. Yeah, this is DFS. Um, hmm. Okay, so I sort of write my own Q code. I'm not sure if that's what everybody uses. Um, I've never read many Q codes, so mine might be very different from what you would find somewhere else. I typically write it like this. Basically, the point is while queue is not empty, you pick up the queue size, you run a for loop for that size, you take out the front, and you pop that element, and then you do whatever you have to do with that. And I mean, of course, you have to do this, and this is something. This would be what your logic in the code where it would be. Might be somewhere inside this also. Okay, cool. Another one done. Path sum. I have also done this on LeetCode. Um, I think I would prefer not writing it again. Given a binary, determine if the tree has a root to leaf path such that the adding up. Okay, so basically you do DFS, which is you go from a root to a leaf, and then you check if it's a leaf node and the sum till now is the target, then you return true. It's fairly obvious. And since you're doing DFS, you're going to be checking every path. So I'm just gonna we just saw something on LeetCode, like some interview experiences. I actually found it pretty worth it to go through these. These actually do give you a good answers sometimes, good questions sometimes. Sorry. Okay, so trees. Um, I think the name is also pretty much the same. Path sum, yeah. Yeah, it was so straightforward. 4 minutes. Yeah, it's a pretty obvious one. What's in it? It's in C++, thank God. Just one sec. I'm getting a call. Yeah, if A is null, return false. Cool. Let's just check if there are some other solutions that maybe say they're better. I don't know why people do this, man. Anyway, if it's null, if the value is sum and both nodes are null, then has path sum. Yeah, okay, so you're just subtracting the current node's value. Yeah, I think that also works. What I did was keep the current sum, I guess, and the target, and just kept a variable to maintain. So yeah, I guess instead of maintain this variable, you could have just done this or this, and that's what this would have returned. All right. Anyway, I guess you get the point. Um, it's been about okay, it's been about an hour and 20 minutes on this stream. I'm gonna take a small break. I have some office work that I need to take care of. Also, my hands are a little tired and so are my eyes. So I'm gonna see you guys in a while. Thank you for joining.